Welcome everyone, my name is Pappik. I'm currently a PhD student at the Hasso-Plattner Institute in Potsdam in Germany, and today I'm going to present our paper A Spectral Independence View on Hard Spheres via Block Dynamics, which is a joint work together with Tobias Friedrich and Andreas Göbel, who are both also from the Hasso-Plattner Institute, and Martin Krejca, who is currently at the Sorbonne University in Paris. Now, in this paper, we mainly get a new algorithm for approximating the so-called hard sphere model, which is a model from statistical physics. However, before we look into this model, I would like to start with a slightly different model, namely the hard core model. The reason is that we will need this model later on, and it's usually more intuitive for computer scientists. So the hard core model is defined by an undirected graph and a parameter lambda, which we assume to be a non-negative real value. Now we define a weight for each independent set, which is basically just lambda to the power of the size of the independent set. So this independent set, for example, would have a weight of lambda to the power of 3. And we now can define two interesting objects, mathematical objects, namely the partition function, which is just the sum of the weights of all independent sets, and the Gibbs distribution, which assigns a probability to each independent set proportionally to its weight. So you see that the partition function is just the normalizing constant of the Gibbs distribution. So what this model basically represents is that we have positions, represented by vertices, that can be occupied by particles. However, as particles need a certain amount of space, no two adjacent positions can be occupied, which is where the independent set structure comes into play. Now you can investigate different properties of this model. One is, for example, the existence of a phase transition. And without going too much into detail what this phase transition is, you can think about this as a transition from having short-range correlations between vertices to long-range correlations between vertices in the Gibbs distribution. But one interesting thing that is known about this is that, for example, for the infinite delta regular tree, we have an exact value for the point of such a phase transition, depending on the degree delta. Now, this has interesting algorithmic implications. So, for example, for a general graph of maximum degree delta, it's known that we can approximate the partition function efficiently as long as we are below the corresponding tree threshold. On the other hand, if we are above the threshold, it becomes NP hard to approximate the partition function on general graphs of maximum degree delta. Now, as I said, this is not quite a model that we were looking into, but the model that we were looking into is sort of where this hardcore model originates from. And this is the grand canonical hard sphere model. So in the grand canonical hard sphere model, we model the distribution of particles with hard constraints in Euclidean space. So this is actually a continuous model. And the way that this looks like is as follows. So we have a region which is bounded and measurable in d-dimensional Euclidean space. And now the assumption is that particle centers are distributed according to a Poisson point process with some intensity lambda, which we call the fugacity. In case you're not too familiar with Poisson point processes, it's actually not that important for now, but one thing that you could keep in mind is that as we increase the fugacity, we get denser and denser point configurations. Now, so far the model would be rather boring as it's just a Poisson point process. However, this is where the constraints come into play. So we assume that particles are actually spheres of a radius r, and now we only allow configurations where particles are non-overlapping. So this configuration, for example, would be invalid as the two particles are overlapping. And now this basically already perfectly defines our Gibbs distribution. And similar to the hardcore model, we can now define the partition function to be the normalizing constant of the Gibbs distribution, where this integral is basically over all k tuples of points, and with some indicator function that indicates whether a certain configuration of points is valid or not based on the pairwise distance of points. And we integrate with respect to the Lebesgue measure. Now this quantity actually encodes a lot of information about different properties of the system, such as the thermodynamic pressure and so on. And this is what we want to approximate. So we want to approximate the continuous hard sphere partition function. For this, we allow ourselves a few assumptions. The first one is that we assume that the region that we are considering is basically a hypercube. And the second one is that we assume that the radius of particles is chosen such that the volume of particles is equal to 1. So the volume of a ball of radius r is equal to 1. The second one is actually not quite a restriction, as if we want to have a different radius, we can just scale the system and the fugacity appropriately. to get a model with particle volume 1 that has the same partition function. The first assumption is indeed a restriction, however, we want to especially investigate up to which value of the fugacity we can approximate this function. Thus, we want to remove additional complexity that just arises from having very complicated shapes in Euclidean space. Also, this is a quite common assumption when it comes to investigating computational properties of this model. Now, quite some work has been done in investigating such computational properties, some of which is rigorous and some of which is non-rigorous. One that I would like especially to emphasize is this paper by Metropolis, which first introduced the Monte Carlo Markov chain method. And nowadays this is a method that basically belongs to the toolbox of most people who are studying randomized algorithms, so there's quite some historical weight to the hard sphere model. A different thing that we can investigate are basically the existence or non-existence of a phase transition. However, it's actually not known whether there is even a phase transition for more than one dimension in the hard sphere model. An ongoing effort is put into further increasing the region for which we know that there's no phase transition. And I especially picked these two papers among many because the last paper is basically the best known bound, so E divided by 2 to the power of D. And these two papers do also something pretty interesting because they basically take tools that were originally developed for the hardcore model in computer science and translate them to the hard sphere model, so that they translate them to the continuous domain. Now, also the last paper raises the question whether we can also get an efficient approximation of the hard sphere partition function if we are below this threshold of E divided by 2 to the power of D. And this is basically what we answer in our paper affirmatively. So our main theorem is that there is a randomized approximation for the partition function that runs on time polynomial in the volume if we are below this threshold. Now, our technique is quite different from what they do, because instead of taking tools that were developed in computer science for the hardcore model and translating them to the continuous model, we go the other way around and discretize the continuous model such that we can apply algorithmic tools that were already developed in computer science. This brings us also to our roadmap. So we start with a hard sphere instance, so some region and a fugacity, and the first thing that we do is that we discretize this continuous model to obtain a hardcore instance. Now we discretize based on a resolution parameter, ρ, and we get a hardcore instance that depends on this parameter, so g ρ as a graph and lambda ρ as a parameter. The first thing that we show is that the hard sphere partition function is close to the partition function of the hardcore representation that we obtain. So this means, especially if we can approximate the partition function of the hardcore representation, we also get an approximation of the partition function of the hard sphere model. In order to approximate the partition function of the hardcore model, we will apply a Markov chain Monte Carlo algorithm, which means that we first have to approximately sample from the Gibbs distribution. However, it turns out that existing algorithms do not do this in the runtime requirements that we have. Thus, we need to extend a method to investigate such Monte Carlo Markov chain algorithms known as the spectral independence method. After we've done so, we obtain the approximation for the hardcore model that we need, which, as I said, also results in an approximation for the hard sphere partition function. Okay, let's just jump right into our discretization. As already said, we discretize based on some resolution parameter ρ, and the way that we do this is actually quite straightforward. So we just divide our region into hypercubes of side length 1 divided by ρ. And what we do now is that instead of allowing all possible continuous point configurations in here, we restrict the configurations to those where the points lay on grid points of this resulting grid. So what this formally looks like is that for a resolution, the set of our vertices contains one vertex for each such grid point, and we connect two vertices with an edge if they correspond to distinct grid points with Euclidean distance less than 2 times the particle radius. Now this already gives us our graph, but we still have to figure out how to choose the parameter lambda ρ, and it turns out that the continuous fugacity divided by ρ to the power of d is a good choice. Just for intuition, why this is a good choice? Basically, in the proof, we want that the grid points represent certain continuous regions, and when doing so, each grid point represents 1 divided by ρ to the power of d amount of continuous volume. So this is sort of how you come up with this way of translating it. Now, if we want to bound the difference between the continuous and the discrete partition function, we will especially be interested in how much can we mess up configurations when we discretize. So how much can we turn invalid to invalid configurations or the other way around when discretizing. And the way that I like to think about this is as moving particles to particle centers to grid points and seeing how much we can mess up their configurations. So for example, assume we have a configuration where we have a particle center in this orange grid cell. We simply move it to one grid point that represents the grid cell. And if we have multiple particle centers, we just do the same thing for all these centers. And of course, there's stuff that can go wrong when doing so. So, for example, assume we have these two particles, which are overlapping, so this is an invalid configuration. However, after discretizing, they are non-overlapping anymore, so this results in a valid configuration in a discrete setting. And the same can happen the other way around. So these two green particles are basically non-overlapping, so everything is fine. However, after discretizing, their discrete corresponding configuration is overlapping, so this results in an invalid configuration after discretizing. However, what should become apparent is that as we increase the resolution, so we make our grid finer and finer, these effects should vanish. So in a limit, we somewhat should get our continuous partition function. And in fact, we can even prove a speed of convergence or a bound on the speed of convergence in terms of the resolution rho. Now, just to get an intuition how this is obtained, as I said, I like to think about this discretizing as moving particle centers to grid points. And what you will see is that you basically only move particle centers by at most 1 divided by the resolution. So the reason is that this is basically just the diameter of a grid cell, which is mapped to a discrete point. Now, what does it mean? Assume we have a configuration of at least 2 particle centers, and assume this configuration turns from an invalid configuration to a valid configuration by discretizing. So this means that initially our 2 sphere centers had a distance of less than 2r because the spheres were overlapping, but it was not less than 2r minus 1 divided by the resolution, otherwise discretizing could not move them sufficiently much apart. And for the case that we go from a valid to an invalid configuration, we basically have a similar inequality. So we know that the initial particle positions were at least 2 times r distance apart. However, it was less than 2 times r plus 1 divided by the resolution, as otherwise we could not make them overlapping by moving them by this amount. So from a different point of view, let's just fix the position of one of the particles, x, and look at this ball of radius 2r. And now we look into this ring of width 1 divided by the resolution, and what we know is that y must be somewhere in this region for x and y to cause the configuration to flip from valid to invalid or the other way around. So what this means, if we just ignore all other particles and only look at each pair of particles and how many possible configurations are there that satisfy this condition, we sort of get an idea of how we can obtain an upper bound on the set of configuration that changes, which gets us an upper bound for the difference of the partition functions. And we can then further bound this to obtain our result. Now we have this result, but what do we actually get as an algorithmic implication from this? So the first thing that we might be interested in is the maximum degree of our discretization. And the reason is that, as we have seen at the beginning, for the hardcore model, our ability to approximate strongly is related to the maximum degree. So this maximum degree is roughly 2 to the power of d times rho to the power of d, which you get by simply counting the number of grid points that are within a ball of radius 2r. Now what we also sort of want is that our parameter lambda rho is below the corresponding tree threshold, because this is sort of the regime where we have a sufficient condition for approximation, and we call that lambda rho is the continuous fugacity divided by rho to the power of d. So this tree threshold can roughly be bounded by E divided by the vertex degree. And what this means is that we can simply rearrange this to see that a sufficient condition for this is that the continuous fugacity was less than E divided by 2 to the power of d. So this is exactly the bound that we wanted to achieve. However, are we done? Not quite, because it turns out that existing algorithms do not run within the runtime constraints that we want. The reason is that existing algorithms for approximating the hardcore partition function has a runtime that's polynomial in the number of vertices. However, if you calculate the number of vertices, this is roughly rho to the power of d times the volume, and we need to choose the resolution rho to be super exponential in the volume in order to compensate for the error term that's caused by discretization. What this means is that also the number of vertices is super exponential, and thus the runtime is not polynomial in the volume. Now let's have a look why this is the case. As I said, we are going to apply a Markov chain Monte Carlo algorithm. So the first thing that we want to do is approximately sample from the Gibbs distribution. And the way that this is usually done for the hardcore model are so-called Glauber dynamics. So the idea is we start with a deterministic independent set. For example, we can just take the empty set. And at each step, we choose a vertex uniformly at random, and we update it with an appropriate probability distribution. So we either add it to the independent set or remove it from our current independent set. For example, we might just start with adding this vertex, then this vertex, and removing this, and adding this one, and we just continue until we somewhat converge to our desired distribution, which is the Gibbs distribution. Now, of course, bounding the time that we need for this convergence is sort of the main mathematical challenge when applying Markov chain Monte Carlo algorithms. However, a different thing that we can see is that, in fact, we intuitively should not assume that we get a runtime that's smaller than something polynomial in the number of vertices. So the reason for this is that we start with a deterministic setting and we want to end up with something that's probabilistic, so a random configuration. Now this means that each vertex should at least have a chance to update at least once, very vaguely. So quite intuitively we should not get a mixing time or a convergence time that's smaller than something that's linear in the number of vertices. But this also gives us an idea of how we can improve on this. And one such way is to use clique dynamics. So clique dynamics is a Markov chain that we introduced in an earlier paper on abstract polymer models. And the idea is that we update multiple vertices at once by using a clique cover. So a clique cover is just a set of cliques in your graph that cover all vertices. And now the idea is quite similar to Glauber dynamics. So we start with a deterministic independent set, and at each step we choose a clique uniformly at random, and we update all vertices in this clique with an appropriate probability distribution until we converge to something that's close to our Gibbs distribution. Now the interesting thing is that you can show that the runtime of these clique dynamics mainly depends on the number of cliques that you choose in your clique cover instead of the number of vertices in total. Now this is pretty interesting for us because I claim that there is a clique cover of size linear in the volume for our graph. Now for this, divide the region into hypercubes of side length less than 2 times r divided by square root number of dimensions. And what you see is that inside such a region, each pair of points has a distance of less than 2 times the radius. This is simply a bound on the diameter of such a region. Now what this means is that no matter how we choose our resolution for discretizing, every pair of vertices that come from such a region will have an edge in between. This is simply how we define the set of edges. And now this means that no matter how we choose the resolution, all vertices from such a region will form a clique. And if we simply count the number of such regions that we need in order to cover our original region V, then we see that this gives a clique cover that's polynomial in the size of our region and the volume of our region. Now finally, there's still one question that remains, and this is whether clique dynamics are also rapidly converging up to the tree threshold. Now this is where the spectral independence part comes into play, and I will not go too much into detail about this, as at this point things get very technical. But I will give you a rough idea of how it works. So the basic idea is to use something that we basically learn in most stochastic process courses, namely that you can represent the transitions of a Markov chain in terms of a linear operator. Now, when investigating the spectrum of this operator, this tells you a lot about the speed of convergence of your Markov chain. However, if you get a sufficiently complicated Markov chain, you will have a hard time solving for the eigenvalues by hand. Luckily, people came up with ways to circumvent this and do so indirectly. and one very recent technique that came up is the spectral independence method. So the idea is to take Glauber dynamics and map them to a random walk on the simplicial complex, where simplicial complex is just some combinatorial structure that is related to a matroid. Now it turns out that you can investigate the spectral properties of this random walk by investigating spectral properties of more local random walks by some local to global translation. And this boils down to investigating a certain notion of influence between vertices in your graph. Now our contribution in this direction is that we construct a simplicial complex representation for clique dynamics, and we use this to relate the spectrum of clique dynamics to a certain notion of influence between cliques and vertices and vertices and vertices. Now our main theorem in this direction is now that the clique dynamics for a clique cover of size m converge in time polynomial in M if we are below the 2 threshold. Okay, so I would like to end the talk with giving you an overview about more recent results that we came up with in the meantime since we submitted. So one is that we actually figured out that we can decrease the number of points that we require for discretization down to something that's polynomial in the volume by using a more involved proof technique. Further obvious open question is whether you can also obtain a deterministic approximation algorithm for the same regime that's polynomial in the volume. And so far we at least have a quasi-polynomial algorithm, but it turns out that it's quite tricky to improve this to a fully polynomial algorithm. Further, a different question could be how to extend our approach to other hard constraint models from statistical physics, and we figured out that for quite a large class of models we can actually do so by constructing a more elaborate discretization. Now some other open questions which we have not looked into yet but maybe planned for the future would be whether we can also extend this approach to soft potentials, so where particles are not explicitly excluding each other but rather have some soft repulsive interactions. And a very ambitious question, but is there any way to prove a computational hardness result for the hard sphere model above a certain fugacity level? So this is very ambitious, as depending on what you believe, this might imply that there's also a phase transition in a physical sense, which would solve a question that has been open for multiple decades. Thank you very much for your attention, and I hope you enjoyed my talk.